In this lecture, what I wanted to do is to give you a flavor of recent advancements in observations and modeling in a coupled way. So in particular, what I wanted to discuss are three things. One is CMB, but not the observations we discussed, the observations on just the optical depth, the CMB optical depth, but something more, which depends on patchy reionization. That is the KSZ signal and B mode polarization, and I will describe them what they are. I also wanted to discuss a bit on quasar absorption spectra, and then at the end, a bit on 21 centimeter experiments, which are ongoing and coming up. So CMB and quasar, all of you will realize that these actually form the basis of reionization. We discussed them in the first lecture. We discussed them in the spirit that whatever is like robust and completely understood, those were the portions we discussed earlier. But now we are going into regimes which are more advanced, more recent, and the work is still, research is still going on there, and there are a lot of work needed. And remember, I mean, CMB basically, the reionization signal is imprinted on CMB because the CMB photons are scattered off free electrons once the universe gets reionized. And the main quantity of interest is still this Thomson scattering optical depth, which we talked about earlier. And I think yesterday you also calculated for in the tutorial for simple reionization models. What you need to understand that this is an integrated quantity and it is less sensitive to the details of reionization process. So it may happen that you have two different reionization histories, but both of them when integrated gives you the same value of tau. The reionization signal will seem to be very similar in these two cases. For example, think of these models. There are three models here. So what has been plotted here is the fraction of mass that is ionized versus redshift. Again, these are the plots you would have obtained yesterday, these kind of plots. But you see, these are three completely different reionization histories, but these three will all give rise to the same value of tau. I mean, like 0.054 in this case, the midpoint value of Planck. So that is the problem. If you just stick to tau, you will maybe miss the details of the reionization history, and also all these the effects of patchiness and all are all gone because this is just one globally integrated quantity. Now, there are many ways in CMB where you can go beyond just simple tau calculation. And one of them is the so-called kinetic Sunyaev-Zeldovich effect. Now, this effect is very well known in the context of clusters, galaxy clusters, but the same effect also works in during reionization. So the idea, the broad idea is this: the CMB photons are coming towards us, and in the middle, it will encounter these electrons. So think of this as some ionized region, okay, which contains free electrons. And of course, there will be scattering, but what you need to remember is this bubble, it will have a bulk velocity, okay, because of this is the peculiar velocity. This is something again you would have done during your large scale structure courses. So it may be depending on, so this bubble may be very close to a massive collection of galaxies, or it may be very close to a void or whatever, and depending on where it is, it may be pulled towards these sources of galaxies, it may be pushed away from the void and so on. So it will have a velocity, and that velocity may have some line of sight component with respect to us. Now, depending on that, what it has, what will happen is it will like the temperature, the temperature of the CMB which we will observe will get changed. Okay, there will be a Doppler kind of effect. So in fact, there will be a change in temperature in a given direction, which will be proportional to the number of electrons you have, because number of free electrons are needed for the scattering. But it also will depend on the line of sight velocity. Whatever direction you are observing, whatever is the line, the velocity along that direction will play a crucial role. So n dot v. So this is basically what, and then there are other factors, but this is the main physical origin of this temperature change. So clearly that will affect the CMB anisotropies, and it turns out that it gives rise to an additional signal, and that signal like becomes prominent at angular scales which correspond to the typical sizes of the ionized regions, and this is something which you can calculate and show. Now this shows the KSZ signal arising from patchiness in reionization. Remember, this signal directly is probing the patchiness. Okay, so that is the advantage of KSZ signal over the other signals which we talked about in the first lecture. So this is the typical strength of the signal. What has been shown here by these different colors is the is for different source models of reionization, and different source model give rise to different signals. Look at the multipoles. These are like 1,000 to 10,000. So this is a really small scale signal, as opposed to the reionization bump, which occurs at much smaller L's of few tens in that case. This is a much smaller angular scale signal, and it corresponds to the typical bubble sizes. This dashed line actually corresponds to the signal when the universe was ionized in a homogeneous manner. So imagine a toy model where all parts of the universe gets ionized at the same time. Okay, so you call this a homogeneous reionization model, and that model clearly doesn't have a prominent signal like this. So whatever you see here is coming from whatever is happening in the last scattering surface. Now I can ask, are there data? In fact, there is already data on this. There is a data point obtained from the South Pole telescope. This has just appeared last year, and that is the data point. It has relatively large error bars, but you can see, you can start like constraining models based on this data point, and hopefully this has more information than the simple tau. Okay, it turns out upon detailed calculation that it doesn't contain too much information compared to tau, but it does have some more constraining power compared to tau. So this is something which we did recently, and what is shown here, that if you just take CMB data, no other data, okay, and try to constrain reionization model using one of the semi-numerical models which we discussed in the morning, in this case the script, you will get constraints on this. Okay, so these are the kind of allowed reionization histories. Of course, this is what you get at present, and then we didn't stop at that. We asked the question that in the future there will be more CMB experiments which will be coming up, and this is like really the next generation of CMB experiments. Lightbird and S4. Lightbird will be like super Planck. S4 will be something stage 4 experiments. And once you come there, you will see that the reionization history can get, in principle, really constrained just from the CMB data. So that is something which is we need to keep an eye on. That CMB data is kind of coming up in the near future, and it will constrain reionization to a large extent. And in that case, if you are really trying to do a parameter estimation, fast modeling may help. Okay, so that's something to keep in mind.
So Tirth, are there any degenerate parameters at such a high L values with reionization?
What do you mean degenerate parameters?
I mean, are there any cosmological parameters that can leave the, do the up and down in the multiple IL?
Okay. No, okay. In principle, yes, because this is convolved with this. In principle, there is this dark matter power spectra also convolved. But remember, when you do the analysis, you will be taking the full CMB data.
Correct.
So cosmological parameters will also get constrained because of whatever other L's and polarization and so on. And then you will add the CMB, the reionization parameters on top of that.
Correct.
Okay, so then any degeneracies will be broken because reionization won't play a role. Let us say along the acoustic peaks, there is no role of reionization there. Okay, but here, so that is how the degeneracies will be broken.
Correct.
To be fair, we didn't do the analysis in a much that sophisticated. We assume that the cosmological parameters are well known at this stage. But I agree that once you come to really serious calculations for these kind of experiments, one needs to do one needs to vary all the parameters, take all the data, and come up with a very proper way of seeing what kind of models you will constrain.
Right.
Okay. But as you can understand, the moment you start varying cosmological parameters, the simulation starts to become, I mean, you have to run many dark matter simulations also. So
Yes.
these things we will take it up soon.
Sure. Yeah.
Yeah, so this is kind of projects in progress because we have many plans. In fact, as I was also saying in the first lecture, CMB, the reionization also generates B mode polarization. Now, this is a B mode signal. So this is B mode polarization versus multipoles. And these lines are for different reionization models. For example, the blue one would be something where reionization is driven by faint galaxies. And the red ones are like, imagine reionization is driven by extremely rare sources. Okay, this is an extreme case like quasars or things like that, which are probably ruled out already from other observations or difficult to accommodate. But just hypothetically, what I'm trying to say is, as you change the source model, the reionization signal can change by like almost an order of magnitude. Now, the B mode actually will be used to obtain the primordial gravitational wave. And this is the signal ignoring the patchy reionization for a typical primordial gravitational wave model for a signal. So this is the so-called tensor to scalar ratio. We took some value. So clearly the reionization signal is subdominant at very large angular scales, but it can start to affect your gravitational wave signal at these scales. So now suppose you don't subtract out the reionization signal properly and just think that whatever signal you have observed is all coming from gravitational wave, you may be actually making a mistake in inferring about the gravitational waves. So this is something one should keep in mind, that one is planning to do a lot of fundamental physics with CMB, and reionization can play a spoil sport. If our luck is good and if the gravitational wave signal is much smaller than what we have assumed here, then you may be actually doing reionization science with B mode, but that may be very far-fetched. So, but again, the point is, with the future CMB experiments, reionization is going to play a big role. Okay, either you will be doing reionization science, or you have to know about reionization and subtract it properly to do other sciences. Okay. Now let us change track. From CMB, let me go to Lyman alpha forest. And now Lyman alpha forest, you remember. Okay, so this, for example, is the Lyman alpha emission line of a quasar. This is a quasar at like nearby universe. It shows almost no absorption. You can see the continuum. And then as you go to higher and higher redshifts, you can see the Lyman alpha forest building up. So this is this absorption. And by the time you hit redshift 6, you see like complete darkness, okay, or then some small spikes on top of that. But of course, we have understood that the complete darkness doesn't necessarily mean that it's a neutral medium. Even a 10 to the minus 4 neutral fraction can give rise to these complete absorptions, okay. So this is something we did earlier, and we said that, oh, now Lyman alpha forest becomes a bit difficult. We don't know what to do from here. I don't know whether it is 10 to the minus 4 or 10 to the minus 2 or 1 or what. Okay, so we have to do something more from there. So then clearly we have to do something which is just not like calculating an average and just trying to do some order of magnitude calculations and things like that. You have to do some more sophisticated statistics. And one of that which is coming up is that people went and took regions. Okay, so you take this region, so all these regions are roughly of the order of 50 H inverse co-moving megaparsec along the line of sight. Remember, these are spectra, so you're observing along the line of sight. Now, in each of these regions, you average the transmitted flux. Okay, let us call it average F, an average over 50 H inverse regions. People love to work instead of this F, people have to work with a quantity which is called effective optical depth. Strictly speaking, this is not optical depth, because optical depth is e to the minus tau. What you are doing is you're taking e to the minus optical depth, averaging it, and then taking a minus log. So it is not really the average optical depth. So you should be careful about that. But this is something, okay? It's an effective optical depth, but it measures basically the transmitted flux in each of these regions. Now what will happen is there are many quasars which you see at high redshift. And what you do is for each of them, you break into chunks of 50 H inverse megaparsec and calculate this number. Now, if the universe is reasonably kind of homogeneous at the redshift you are interested in, all these 50 H inverse megaparsec regions will give you all more or less the same value of this, okay, because you are averaging over that. However, if the universe is patchy, and patchiness at scales of 50 H inverse megaparsec, you may find like this distribution, this quantity, the distribution has a weight, okay? It's not like all these chunks are not giving you the same value, okay? They are giving a wide range of values. And this is what was done in 2015 first by Becker, and then various other people did much more analysis with more data. So what has been shown here is the cumulative PDF of this quantity. Okay, so this is at low redshift, around redshift 4, and then it is 4.2, 4.4, and you come up to something like redshift 5.8. What you find that at low redshift, you see the cumulative PDF is almost like a step function. Cumulative PDF step function means the PDF is almost a narrow delta function like. So that is what you expect from a homogeneous universe. All the chunks give you almost the same value. As you come to higher and higher redshift, now here, for example, take the highest redshift, you should look at this red line. You will realize that this is clearly not a very sharp, like narrow distribution. This has a width. So if you go and calculate the PDF, which is derivative of that, you will see it's a bell-shaped but reasonably wide kind of distribution. Okay. So clearly this now needs explanation. And in fact, when people compared with simulations, people realized that models which had like uniform radiation background cannot match the data beyond redshift of 5, and that led to a lot of speculations in the field, like what gives rise to these fluctuations. And many people did that, and one of these things were done by Girish Kulkarni and his collaborators. So they came up with a very, advanced radiative transfer simulations, like the simulations we were talking about in the morning, full radiative transfer simulation. Theirs were moment-based method. And then they showed that if you just delay the end of reionization, so what has been shown here are light cones, and you just concentrate on this panel, which shows the neutral fraction. And these are basically neutral regions. And as you are coming to lower and lower redshift, this is redshift 5.5. You see, even at 5.5, there are some neutral regions which are left over. So reionization is completing somewhere around 5.4 or so. And if you take such a model, you are able to match the distribution. So this then was interpreted as that you are actually observing final stages of reionization. What we wanted to check is, since we had access to fast models, we wanted to vary like all the parameters and see how robust this conclusion is, because they could run only a few models because of the expense in the simulations. But what we can do is we can run. We can just vary parameters, run. We can do a parameter estimation kind of a calculation. So once we did that, what we ended up, so you can ask, what is the challenge in doing that? The challenge is, what happens is in default versions of the semi-numerical model, in script or all the other semi-numerical models of reionization, what we do is typically the ionized cells, like whichever cells cross the barrier in an excursion set, or even in our case, we just count the number of photons. Those ionized cells are assigned a neutral fraction equal to 0. In reality, it won't be 0 because of some recombinations happening. Okay, so it will have some very small fraction, 10 to the minus 4 or maybe less, or something of that order. Okay. So that needed to be modeled, and that requires some extension to whatever semi-numerical model we discussed. Okay. Again, I won't go into the details of this modeling, but it requires some understanding of how to do radiative transfer in these cases. You just look at the map. So this is at redshift 5.8. This is the neutral hydrogen map. So it's basically, this is the neutral island, basically. Small regions of neutral patches remaining, and most of it is ionized. These dark blue parts are all ionized. If you go and observe the, for example, the photoionization rate, of course, in neutral regions, there is no photoionization. There is no radiation. If there was radiation, why would they be neutral? They would be ionized, right? So there is nothing. In ionized regions, there is photoionization rate, but it is not uniform. You see very close to these neutral islands, you see that the photoionization rate is slightly smaller than at larger distances. And this is happening because of some shadowing effects. These points, being very close to neutral regions, won't be able to receive photons from, let us say, sources sitting on the other side of the neutral region, okay, because the neutral regions will absorb those photons. However, sources which are sitting far away from these neutral regions will be able to receive photons from many sources. So this is basically, this is slightly like non-trivial to model, but we could do that, and we could still retain the like efficiency of the code. The code is still fast, okay, but we had to do a lot of approximation and analytical calculations. But at the end, we got a model which can match the data. So the red ones are the data. So the two red ones are like how you deal the non-detections in the data. So let me not go into the details, but this is how it is. And depending on which data set we take, we can match that data without any difficulty. I mean, by varying the parameters, and we can then get the best fit parameters, the 1 sigma errors, and so on. And from that, we can find out what will be, for example, the allowed reionization history in particular, what will be the ionized fraction as a function of redshift. Look at the redshift range. This is late stages of reionization between 5 and 6. And you can concentrate on the red points, for example. So this, for example, is red points with error bars gives us the typical reionization history that's allowed by the data. Okay, so this is where we are. We can actually go and now start constraining the final stages of reionization history using the quasar absorption, the Lyman alpha absorption. So in the earlier part, I showed how to constrain reionization history using in recent and upcoming CMB data. This is showing you how to do that using quasar absorption. Of course, ideally one should like match, I mean, actually use both the data sets simultaneously and do that. But that comes with their own modeling challenges, and that's something which we are looking into at present. Okay, so again, as I said, these are things which are happening. This is really current research area. But given this, I mean, you can ask then the kind of reionization history you get. I mean, how does it look like? And again, you would have seen these things a lot of time, but this is a typical reionization history. So we can start at redshift 15, where almost nothing is ionized. So what is shown here is the neutral hydrogen map. Okay, so take a slice from the simulation box and show the map. So at early stages, this neutral hydrogen is following basically the underlying dark matter distribution. And then I mean, so the redshift you can see is changing and the Q is increasing. And at some point you will be able to identify the bubbles clearly. So these are places where galaxies have formed, and you can see these black regions are basically holes in the neutral hydrogen. Okay, these are getting ionized. And then these black regions are clearly growing. Okay, they are growing. And then if you just keep an eye on one of these black regions, you will see they start overlapping with other black regions. Okay, so this is how reionization progresses. You form individual bubbles, they grow and then they merge. Okay, so there is a merging, and from small bubbles you go to larger and larger bubbles. Okay, these are similarities with hierarchical structure formation. Okay, so there are a lot of similarities here. There are a lot of similarities in modeling as a result, but yeah, that's also something which this is something people are worrying about and should worry about. Okay, and then I keep on moving, and at some point you will see the universe becomes like black. It's completely ionized. So basically you have these bubbles growing, merging, and ionizing the universe. Now we can go and spend some time on the 21 centimeter signal. So this is a school on 21 centimeter, but I realize that I haven't really spent much time on 21 centimeter signal. So, and I'm going to spend not much time also on the 21 centimeter signal, because what you realize is, in addition to the 21 centimeter, there are also many other observations which are happening now. So if you do reionization modeling, the scope is really wide. Okay, I mean, you can already start playing with the models. And by the time the 21 centimeter data really becomes competitive, you will be in a good position to deal with that. The 21 centimeter signal of H1 will be observed using low frequency radio telescopes. It will be observed as a contrast with respect to the CMB. So basically the CMB photons are coming from the last scattering surface to us, and they will pass through regions of H1. And three things can happen. Either the H1 doesn't do anything. Maybe it adds and subtracts photons by equal amount. Then you don't observe any signal. Okay, this, for example, can happen during stages of dark ages and so on. The H1 may on the net absorb photons. Okay, so then you will see them in absorption. This, for example, happens during cosmic dawn. Okay, the famous ages signal is an absorption signal. And then it can add photons to the CMB. So then you see the signal in excess, that is in emission, and that is what happens when the gas is heated up, and you see so this will happen. This is the case during epoch of reionization. So I won't go into, I'm sure when you did listen to the lectures on 21 centimeter physics, some of these have already been done. The concepts of spin temperature, the level populations and things like that. The signal which we are after will be essentially proportional to the amount of neutral hydrogen and then this factor. 1 minus the CMB temperature divided by the spin temperature of neutral hydrogen. And what happens is, if the gas is heated up and the temperature is Lyman alpha coupled to the gas temperature, the spin temperature is Lyman alpha coupled to the gas temperature, and the gas is heated up, this T spin will be much, much larger than TCMB. So the factor here in the brackets will be 1. So the signal is essentially proportional to rho H1, and that's wonderful. Okay, so whatever H1 maps we made is actually equivalent to the 21 centimeter maps. Okay, so the 21 centimeter signal is exactly tracing the H1. That's good. And then what you can do is you can calculate various observables from there. And these observables, for example, could be the power spectrum. And that is the first set of observations one is talking about. So I can go back to the same model again. This is the map and this is the power spectrum. So power spectrum of H1 versus K. So these are large scales, small k. These are small scales, large k. And initially, this power spectrum will be essentially the dark matter power spectrum and nothing else. Okay. But as you evolve, this signal kind of changes. For example, it goes down because of ionization, but it also changes shape, okay, because of this formation of bubbles. The formation of bubbles, because they are so patchy, they are so inhomogeneous, basically they start driving the shape of the signal. So now you see the signal is going up as you are approaching neutral fractions of the order of 30, 40, 50%. By the time you hit 40, 50%, the signal is maximum. Okay. You will also see that the position of the peak also shifts toward larger and larger scales, that is an indication that the sizes of the bubbles are increasing. Okay, you will see it's a slowly shifted. Okay, now it has shifted to the left, but now the signal is going down because the universe, when it is 50% ionized, is really patchy. 50% ionized, 50% neutral. But the moment now you make it's more and more ionized, the patchiness is going down. It is going towards again a more homogeneous distribution. And then the signal starts to go down because you are depleting the universe of H1, and it then vanishes. Okay. So clearly this power spectrum has a lot of information about the reionization process, and the 21 centimeter community is planning to go and detect these power spectra. Okay. There are a lot of efforts. I won't have really time to go through all the efforts and their progress now, but let me just talk about a few briefly, a few points about the 21 centimeter experiments. So first thing, the importance of 21 centimeter experiments for reionization is that most of the models which we discussed about patchy reionization were actually motivated by then upcoming 21 centimeter experiments. So that's why the names like 21 centimeter fast and things like that. But of course, when after people develop these patchy reionization models, they immediately realize that they can be applied to many other probes of patchy reionization, which includes the CMB and Lyman alpha absorption. And there are other things which I, by the way, didn't talk about, like Lyman alpha emitters and so on and so forth. So that is one thing which we should keep in mind, that these models started becoming important because of the 21 centimeter experiment, the planning and so on. Now the 21 centimeter experiments have, there is a significance which you should try to understand. If we think that CMB and Lyman alpha are very good probes of reionization and they are complementary, let us look at them a bit critically. CMB, it's a very good probe of ionized universe, but remember it probes the integrated history, at least at the level at which it is working. With future experiments, this may change, but then we have to wait till the future. Okay, the KZ signal is just about coming up and so on. So CMB probes the integrated history. The Lyman alpha absorption in that sense is good. It's a line transition. So depending on at which frequency you are observing the signal, it will tell you at what redshift the signal is coming from. So then you can build up in principle the evolution of reionization redshift by redshift. Okay. However, the Lyman alpha absorption, the transition is very strong. So as a result, by the time the universe becomes even slightly neutral, this probe starts to become more and more insensitive. You can do still something, but then those things you have to really build models and so on. This is where 21 centimeter is actually very exactly what you want. You wanted a signal which is a transition which is line transition, so that you can track the signal as a function of redshift. So 21 centimeter radiation is a line transition, but it is also weak. Being a forbidden transition, it's a hyperprime transition which is forbidden. You know it comes from coupling of electron and the proton spins. So because of its weakness, it's ideal for probing reionization when actual reionization is happening, like when the universe is 50% ionized or something like that, because by that time Lyman alpha will be completely absorbed. Okay. Assuming you can even observe that. Now the H1 fluctuations can be nicely probed using low frequency interferometers. Okay, so we are talking about fluctuations now, and then you have to go to interferometers and then probe it. There are already very good experiments which are ongoing. LOFAR and MWA are like driving the field as we speak today. Okay, so they are it's a big challenge, of course. So they have made a lot of progress. We can already start ruling out extreme models of reionization using the data. but still it's the signal is still orders of magnitudes above the cosmological signal which we are after. Okay, there are also kind of some work with UGMRT. There are telescopes which are coming up like ARTFAC and so on. So it's a very like active field of research in that sense. Of course, the future will lie in like more upcoming and planned telescopes like the HERA and SK, in particular the SK low in Australia, okay, dipoles in Australia. I said the first target will be to obtain the power spectrum because that will have the best signal to noise ratio. Okay, you will really compress information to only few bins. So you really gain a lot there. And that is the first target undoubtedly. But then there is a lot of information beyond the power spectrum because this is such a non-Gaussian, like non-linear field. So with better sensitivity, you may be able to go beyond power spectrum. You may be able to do bispectrum. You may be able to do like more complicated statistics like shape statistics. You can go and even try to image the field. Okay, that's the hope with the next generation of telescopes like the SK. The challenge is severe because the data is humongous. The amount of data you will be dealing with, and then the signal is buried within foregrounds, okay, which are like 4 or 5 orders of magnitude larger than the signal. So you have to really model the foregrounds properly and find ways to subtract them or avoid them, depending on what approach you take and how your telescope is. Okay. At the same time, you need accurate and efficient theoretical models so that the interpretation becomes reliable. Basically, it should not be that you are using wrong models and inferring biased conclusions. So this is basically where 21 centimeter experiments are. I didn't want to go into these with too much details. You must have heard a lot about how these 21 centimeter experiments are doing. And I also wanted to finish a bit early so that you have enough time for either questions or the tutorial. Okay. So I will now just summarize the take-home messages for this lecture. Basically, we have many useful probes of Apache reionization, and 2 of them are CMB and Lyman alpha absorption. Particularly in CMB, we have the KZ signal and the B modes, and in Lyman alpha absorption, you would need to go to the fluctuations in Lyman alpha absorption, whatever statistics you are interested in. And future probes, many of these CMB and other things will also have future probes, but the thing which will probably revolutionize and will really help in understanding reionization will be the 21 centimeter surface. At the same time, there is a lot of scope. There is a lot of scope in building models with different kind of physics included, because we are really struggling with making efficient models, which also has the physics. So if we include physics, the models become slow. If we try to make the models fast, we have to make approximations and so on. So these optimizations have to be done. So there is a lot of work still needed before the SK comes up. So let me stop here. And if there are questions, we can take them, or otherwise we can go to the tutorial.
Yeah.
Okay, Prakash, I guess. Yeah, go ahead.
Yeah, so I was curious about this KSZ effect.
Yeah.
You mentioned that it depends on the velocity of the electron along the line of sight. So if the temperature of the IgM is large in the ionized region, then it can also affect the KSZ signal, right? So it is degenerate between the reionization history and thermal history of the IgM. Is it true?
Sorry, what is large?
If the temperature is large in the ionized region, the velocity of the electrons would also be large, right?
No. Okay. So this, so what you are talking about, that is the thermal KSZ effect, which is, no, that is less effective in this case. Okay. This is talking about the bulk velocity. Okay. The full cloud is moving with a velocity. So we are not talking about the random velocities inside. So this is the velocity which is really the peculiar velocity of the the cosmological field.
So CMB, I mean, this experiment is not sensitive to the random motions of the electrons within the cloud?
Yeah, so not at these scales. So no. And the thermal KC effect from reionization is really small. So you have to go to really high temperatures like clusters to see the thermal KC effect. Okay, so 10 to the 4K is just not enough.
Not enough. Okay.
Yeah. To give a prominent signal.
Correct.
That's why people go for thermal clusters.
I have a related question.
Yeah.
Why we are not considering other particles in this effect other than electrons like neutral hydrogen or?
Yeah, so basically you need something which will scatter CMB photons, and CMB photons are scattered only from ionized species, either electrons or protons, but the cross section goes as inverse of mass of the scatterer. So basically the cross section is much larger, like 1,000 times larger for electrons than protons. So that is why most of the scattering of CMB photons will happen from electrons. So that is the most prominent effect. So that is why we consider only electrons for during reionization for studying CMB. Next question, I think Orghodip, you had a question.
Hello, am I audible?
Yes.
Okay, so I just missed a short thing, which is that you have mentioned that with increasing the ionization fraction value, the peak of the 21 centimeter power spectrum tends to shift to the lower K values, right? So what does that physically mean?
Okay. So the peak of the signal actually corresponds to the typical sizes of the ionized regions. That is where the signal is expected to peak. Mind you, there are other effects also, but that is the prominent, like visually prominent effect. Now, as reionization progresses, the sizes of the ionized regions grow. So that is why the peak of the signal will tend to move towards larger scales. Larger scales means small k, so it moves roughly leftwards. So that is the physical reason.
Oh, okay.
Choudhury, please go ahead.
Hi. So when you do CMB, we only talk of tau as the parameter for the reionization model. But when you're talking about model building for, the simplest reionization model will have how many parameters? Is it only tau, or is there, just like we have 6 parameters for CMB, do we then include a model with, I don't know if my question is well formulated, but.
Okay. So suppose you want to build a reionization model and constrain by matching with CMB data. And for the moment, let us leave out the KZ signal for the time being, because that brings more complications. But let us say you are talking about the standard Planck data is given to you, CL versus L, and you want to constrain reionization. What should you ideally do? You should vary all the 5 cosmological parameters, okay, assuming flat lambda CDM, that is omega m, omega b, the power spectrum normalization, the power spectrum slope, and the Hubble parameter. The 6th parameter is tau. You don't take tau as a free parameter. What you do is, instead of tau, you use some reionization parameters. This could be mass of halos which are ionizing, the reionization efficiency parameter, maybe the clumping factor of recombinations, and so on. So then you vary all these 7, 8 parameters. So 5 cosmological and 3, 4, 5 reionization parameters. And then you try to match the whatever data you are matching. So this would be the ideal thing to do. And this we have tried to do using analytical models. So if you look at the paper by Otridev Chatterjee, which is the most recent work, this is what we have tried to do. And that will give you constraints on cosmological parameters and on reionization parameters at the same time. And it helps if you add some reionization data sets as well, like the Lyman alpha forest and so on. So because otherwise the degeneracies are not properly broken. But many times when we actually do this more sophisticated modeling, varying these cosmological parameters becomes a nuisance basically, because you have to run simulations and so on. So then you have to do some compromises. But ideally, that is what you should do.
Okay. So like 3 or 4 more parameters for.
Yes. Yeah, that will depend on now your favorite reionization model. In our models, we now do, I think, 4-parameter modeling kind of a thing. Yeah.
And I mean, this might be another silly question, but do you have to worry about lensing of this signal? I mean, with CMB, of course, there will be the CMB lensing. But does it make sense to ask about?
Yes. So in principle, yes. But the CMBC, sorry, the lensing signal actually affects scales which are very different than what is where the reionization bump occurs. However, for doing KZ signal and also B modes, you have to worry about the lensing signal, because lensing gives rise to B modes, and lensing also has signal at these scales. So you have to de-lens the signal first.
Okay.
Yes, you do have to worry. You are correct. So here, most of the time, we assume that people have like de-lensed to a very high degree of accuracy.
Right.
Yeah.
Okay, thank you.
Yeah. Fazlu, yeah, go ahead.
I don't know if I missed in the first part. So we were speaking about the evidences of patchy reionization, right, with KZ and 11 alpha. So why don't we speak about the reionization bump from E modes? So is it because it's an integrated effect, or like the tau, we can constrain only tau from there and it's an integrated effect?
Okay, so let's see. So why? Okay, so I talked about TT modes and B modes, but why not E modes? There is no obvious signal of patchy reionization on E modes, unfortunately. Okay, so I mean, there are many things patchy reionization can do, but none of them. So suppose I take a model of homogeneous reionization and a model of patchy reionization, both producing the same tau. There is nothing almost which will change in the E mode signal, unfortunately. Yeah, there won't be anything which changes. No, I am wrong. There will be a B mode like signal like this on the E mode as well. Okay, but that will be way subdominant compared to the standard E mode reionization bump signal we see. So that is why in E mode, the patchy reionization doesn't play a big role. Okay, so there will be a signal like this in the E mode also, but that will be really buried in the E mode standard signal of the reionization path. Okay. So that is why B modes and the TT, but that is also this KSZ which becomes important.
Yeah. Okay, so just a follow-up question. So we saw B mode effects. So these B modes are like E mode getting converted to B mode, like what we see in CMB lensing?
No. These are you can actually generate at parity violating anisotropies because of this cross section, the angular dependence of the Thomson scattering cross section. Okay. So I mean, so let me think a bit. This is. I mean, to start with, you need a quadrupole anisotropy in the CMB.
Yes.
So you need a quadrupole temperature anisotropy in the CMB, but that's all. From there, you can generate both E mode and B mode polarization.
Yeah, I was particularly asking about how patchy reionization B modes are generated. So
yes, that's what the patchy reionization B modes. Basically, they're coming from the see. At a global level, there is no B mode signal from patchy reionization because you're not violating parity. But at different scales, there could be like local violation a parity. I mean, some things, I mean, in some places things are moving preferentially in some direction and some places preferentially moving in some other direction. Okay, so that is the basic idea. Because there are local motions which are happening, these velocities and anisotropies and so on. So you can get B modes, parity violating B modes from patchiness in reionization. So that is how it arises.
Okay.
Yeah.
Thank you.
So Tirth, in the case of KSG effect, are the foregrounds important? Are the
Yeah, very much. Yes.
And how much they are important? I mean, in your analysis, do you neglect them here?
Yes, because these guys, when they come up with the data points, the assumption is they would have subtracted foregrounds as best as possible. And whatever is remaining, they were able to account for in the error bars.
Okay.
Okay, so this is the assumption. We really didn't go and look into the foreground modeling, what they did. Correct. Remember, these experiments are going on for quite some time, many years now. So only the detection has come only now. Till before this, these telescopes were giving only upper limits. Correct. So they were not able to reduce the noise properly, although they observed for many years. So yes. So the foregrounds are have gone into the noise in some sense.
Yeah. Thanks.